Next example on optimization. A box is to be built from a rectangular piece of cardboard. We've got the dimensions, 25 centimeters wide, 40 centimeters long. We're going to cut out a square from each corner and then bend it up at the sides. We need to find the size of the corner that will produce a container that will hold the most amount of soup. Most amount of soup. We want to maximize, again, volume. That's what we're trying to maximize. So let's draw a picture. We've got a rectangular piece of cardboard, 25 by 40. We're going to cut out a square from each corner, and somehow we're going to put super hot soup into the cardboard, and it's going to be all good. And it's a square, so the dimensions of each of these little guys are x by x. Maximizing the volume. Volume. Length times width times height. Well, this length is going to be 40 minus 2x. This width, 25 minus 2x, right? Because we're going to lose an x here and an x here. And times the height, x. Now, this is beautiful because there's only one variable. Good for us. We need to find the derivative, but this is too much product ruling happening. And so we can do a little bit of distribution to make our lives a little bit easier. This is 40 minus 2x and 25x minus 2x squared. And then we'll find that volume equals 1000x minus 80x squared minus 50x plus 4x cubed. So I just like it in standard form. It just makes me happy. I guess you don't really need to do that. But we do have these like terms. Maybe it is a good idea. And that'll give us plus 950x. Whoops. Hold on. Whoops. Hold on. 1000x. 80x squared. Oop, that's an x squared. So I had the wrong like terms. Volume. 1000. Oh, I want it to be just, I like it be prettier. Volume equals 4x cubed. These are my like terms. What is that? 130 minus 130x squared plus 1000x. Okay. Now let's find the derivative. Because now it says product rule minus 260x plus 1000. We want to figure out when that's equal to 0. Ooh, we can divide everything by 4, both sides. We'll get 3x squared minus 65x plus 250 equals to 0. And then you can solve this how you want. Factor quadratic formula. I just so happen to have the factoring on my paper. 3x minus 50, x minus 5. So x is equal to 50 over 3, or x is equal to 5. Let's see. So now we're going to make a number line for v prime. The lowest volume we could have doesn't really make sense in this context, but I guess I can mark the 0 if I wanted to. Whatever, 0. Then comes the number 5. 50 over 3 is bigger than 5. So say we test the number here. Say we even test the number 0, because that's super fancy. Not fancy, handy. Handy, it's handy. Okay, you plug in 0 here. You're going to have 0 and a negative, 0 and a negative, negative and a negative. Positive. Say you plug in x equals to 6 here. If you plug in 6, you're going to have a negative and a positive, so that's a negative. That's okay. And we plug in some number way out here. Say we plug in, 20. It's going to be a positive and a positive. Here is a positive value. So the question was, find the size of the corner square where you'll be able to make a container that holds the most amount of soup. So we want a maximum, changing from increasing to decreasing, positive to negative. So we've got a corner square of x equals 5 centimeters will maximize the volume of the soup container. It'll maximize the volume of the soup container. Cool. Okay. Let's go on to example number 3. A rectangular page is to contain 24 square inches of print. That's area. Area is 24 square inches of print. Margins at the top and bottom are to be 1.5 inches, so that's top and bottom. Margins left and right at the sides are 1 inch, top and bottom, left and right. The question is, what should the dimensions of the page be so that the least amount of paper is used? Least amount of paper is used. So we're talking about area again. All right, so what do we know? We know that the area is 24 square inches. We know stuff about the margins. 1.5 inches, top and bottom. 1 inch at the sides, left and right. We want the dimensions so that the least amount of paper is used, right? Area, so this is 24 square inches of print, right? That's where you can type or write whatever you want. And we are trying to optimize area, and we want it so that it is a minimum. We want to use the least amount of paper. We're trying to be conscientious of the trees. So let's draw this picture. We've got a rectangular piece of paper, and we've got some sort of margin action happening here. And so the margins on the side, that's 1 inch, right? This is a length of 1 inch. Top and bottom, 1.5. That margin is 1.5. We need to figure out what this area is going to be. Well, this little dotted one can be x, and this vertical dotted one can be a y. Okay. Now, we're trying to minimize the area for like the really big part of the paper, the whole piece of paper, right? We know what the area of the dotted rectangle is going to be, the area of the whole piece of paper. So based on that, area equals, well, going horizontal, this length here is x plus 1 plus 1, or x plus 2. And vertically, that's y plus 1.5 plus 1.5, or y plus 3. So area that we're trying to minimize is x plus 2 times y plus 3. We also know here that the area where you can print on, area equals, I could do area big and area small, has to be equal to 24, and that's x times y. Now here is where we might do some solving, because this is not the one we want to minimize. We want to minimize this one. We can choose to solve for x or y. I'm going to solve for x. X is equal to 24 over y. I'm going to substitute in area 24 over y plus 2 times y plus 3. And distributing, we're going to have first times the first is just 24. Outer times outer. 24 times 3, that's 72. And this is the same as y to the negative 1 plus 2y plus 6. So we can combine some like terms. 30 plus 2y plus 72, y to the negative 1. Now we've got an equation. It's all in terms of one variable, so which is great. We can find a prime. That's 0, that's 2, That's minus 72, y to the negative 2. And now we want to know, when is this equal to 0? When is 2 minus 72 y to the negative 2 equal to 0? Well, this is 0 equals 2 minus 72 over y squared, right? So we can do I'll add 72 over y squared. 72 over y squared equals to 2. Cross multiply. Y squared equals to 36. So y is equal to 6. I'm not including the negative one because of context, right? It wouldn't make sense to include negative 6 because we're talking about area and dimensions. So number line, this is for a prime. We can start at 0, and we're going to test 6. Say we test y equals to 1, wherever you want to test it for a prime. If we plugged in y equals to 1, we're going to end up with a negative value. And maybe over here we go ahead and we test y equals to 7. It's going to give us a positive value. So meaning the graph of the area function will go from decreasing to increasing at x equals to 6 or at y equals to 6, making this a minimum. So we can say area of paper is at a minimum when y is equal to 6. And then we could just go ahead and solve for x, right? If y equals to 6, oops, coming over here, excuse me. If y equals to, y equals to 6, then x equals to, what is x equal to? X equals to 4. Oops, can't read my own handwriting. Yep, 24 over 6, x is equal to 4. These are the dimensions that will minimize the area. Okay, I got 2 more examples for you coming up next.